Well, what is numerology? Numerology tends to be, oh, I notice that this thing in the world, like the mass of the muon divided by the mass of the electron, which is roughly 206, that really that that ratio is actually very close to the square root of pi divided by 7 to the power 3, who knows what, something that's just pure numbers. So numerology is the real is sort of the correspondence between things that are purely made of numbers and things that you see kind of in the real world. That's the most common use of that term. Occasionally, there's kind of within mathematics numerology. People notice that there is some kind of coincidence that, oh, this series of numbers that appear in this mathematical problem are the same series of numbers that appear in that mathematical problem. There have been a number of cases, most notably in studying large finite groups and things, where that kind of numerology has paid off. We're noticing in mathematics that this sequence is the same as that other one, that then a connection was found between the source of those sequences. Numerology has a much less good history in natural science, and even worse history probably in kind of more human oriented areas. It's kind of, there are many examples of people trying this. It's really basically, as I'm thinking about it, I don't think it's ever worked. One thing that's often the target of this is a thing called the fine structure constant, which is a characterization of the strength of electromagnetic forces. It happens to be dimensionless. It's just a number. It's roughly 1 over 137. And people say, well, we should be able to just derive this from something lower level. If we have a fundamental theory of physics, for example, we should just be able to derive the fine structure constant. And one day I would hope that our theory of physics will be able to do that. It's worth realizing, just sort of a footnote to that story, is that the fine structure constant as a strength of electromagnetic forces really depends on the observer observing those forces. The value of 1 over 137 is only really correct for an observer that's operating in a sense at very low energy, an observer who, in the uncertainty principle, kind of relates energy to length scales, an observer who is kind of measuring electromagnetic forces on a very large length scale. As you probe them on shorter length scales, the effective value of the fine structure constant changes. So it's a little bit tricky to just sort of say, oh, well, we should have the fine structure constant just fall out of the theory. It's the thing that falls out of the theory has to be something whose value depends on the observer who's observing the thing. But in any case, there's sort of an effort to it's not been a good story. People trying to find, oh, it's really square root of pi times this and that and the other. Now, it's worth trying to understand the sort of theory of numerology. I will tell you something that if you type into Wolfram Alpha some just random number, 1.7284643 or whatever, it will have a pod that comes out that lists possible closed forms. It will tell you what ratios of pi's and things like this are close to the number you typed in. Now, it has a bit of a trade-off because you could get something that's exactly the number you've typed in, but it's a sum of 8 powers of pi divided by lots of powers of e and so on. It could be a really complicated formula. It's sort of completely unsurprising that there is a really complicated formula that represents, the 6 digits you typed in of that number. After all, if we really wanted a formula for the number 1.17 or something, the formula will be 1 plus 1 over 10 plus 7 over 100. And that's a nice, in terms of whole numbers, formula. It's just not telling one very much because that really is just the number you put in. Now, if the number that I put in was 3.14159, then it might be telling me something to say that's just pi. I could say that number is 3 plus 1 over 10 plus 4 over 100 plus whatever, but that's a kind of a long description of the number. the thing that's interesting is if there's a short description of the number in terms of things like pi or whatever else. In a sense, the mission of numerology, I suppose, is to say, is there a small formula for all the digits that you know of that number? It's kind of a thing where it's like asking, you can think of that powers of pi or whatever else as like a program for making the number. And so essentially numerology is this question of, is there a short program that makes my number? I can clearly have a program that's about the same length as the number itself that just writes down the number, but is there a short program that makes the number? Now, even that's a tricky thing to say, because the question of what kinds of operations can be in that program. For example, I talked about pi and so on. People have heard of pi, but how about if I talk about, I don't know, next level of obscurity would be the Euler-Mascheroni constant, or another level would be, the Madelung sum of some lattice. These are all kinds of things that can be thought of as mathematical constants, but they have an increasing level of obscurity to them. And so then you have the trade-off of, well, how many pi's is one Madelung constant equivalent to? Because if I introduce obscure enough constants, then again, I'm kind of, for example, I could just invent a constant that is my personal constant, that is the number I just typed in. And then I've got a very short description, but you don't know what my personal constant is, that you have to have a whole sort of chain of knowledge of that. So in a sense, sort of the question is, if you have a certain language for describing your number, that might include pi's, square roots, things like that, how small can the description of your number be? And that's a reasonable question. There are clearly, if you think about all possible numbers, most of them can't have short descriptions, because those short descriptions are much fewer in number than all the possible numbers with all their digits. But this question of sort of how much is a pi versus, what's the effective sort of description length of saying I've got a pi, as opposed to I've got a Madelung constant? Interesting question. Not obvious what the answer should be. Like 15 years ago, when we were building that capability in Wolfram Alpha, what we did was this. We looked at basically all kind of easily available math papers, academic papers, and we simply say, how often do these constants appear? Pi appears all over the place. The Euler-Mascheroni constant, much less frequently. The Madelung constant, even much less frequently. And then what we said was, let's say that the sort of effective information content of saying it's pi is much smaller in proportion to how much more frequently it appears in mathematical literature. Like if I say it's pi, I probably don't have to tell you any more. If I say it's the Smith constant, I'm going to have to define what I mean by the Smith constant. And so that was sort of a way of getting a proxy for sort of what the effective amount of information associated with saying it's constant such and such. Now, having thought about that, you're kind of in this position of saying, well, if I've got some number that I just measured in the world, how small a program can I make for that number? And is that significant and so on? And if I have that small program for the number, can I imagine a mechanism by which that number would be the value that it is? Let me give you an example within mathematics. If you look at a pair of numbers, let's say 12 and 4, okay, or 12 and 8. Okay, 12 and 8 are not relatively prime. What does that mean? It means there is a divisor of 8. 8 is 2 times 4. 12 is 4 times 3. Okay, the 4 is in common between those. So those numbers have a divisor in common. They are not relatively prime. If we were to talk about, let's say, oh gosh, let me not fail my arithmetic here. Let's talk about 10 and, what's a good example? 10 and 21, okay? 10 is 2 times 5, 21 is 7 times 3. I'm so proud of myself. I'm now beginning to know my multiplication tables. I didn't know them when I was a kid. I've gradually learned them over the course of my life. But in any case, 10 and 21 are relatively prime because they have no factors in common. Okay, so I can ask the question. Let's say I try a whole bunch of different numbers, and I ask, what's the chance that two numbers are relatively prime? And the answer, I'll get some number. I forget what the exact number is, but I go in and get more and more and more digits. And then maybe I type it into Wolfram Alpha and I say, what is this number? It's going to say it's 6 over pi squared. Well, that turns out to be a piece of numerology that works because it really is 6 over pi squared. And there is a mathematical argument for why it has to be 6 over pi squared. And so that's a case where sort of the numerology works out. And as I say, sometimes it does in math. I'll mention this question of kind of numbers and kind of how producible is that number. So let's say that I've got a number and it is producible as 6 over pi squared, for example. I can imagine that if I'm just looking at all possible numbers, I might type in 6 over pi squared and that might be the number I generate. But let's say that you've just got the number 1.73842654379, whatever. I don't think I'm very good at generating random digits, but it's just some sort of randomly generated sequence of digits. Is that number a readily producible number, or is it a number that doesn't have a short formula that I'm ever going to encounter, and it's really a number that I'm very unlikely to find? Is it a number whose chance of occurring is about proportional to 10 to the minus the number of digits that I've specified? So you might say, why would anybody care about knowing whether a number is producible in that sense? I'll give you an example. Back in the early 1990s, there was a big disaster. Intel, semiconductor company, had made the Pentium chip, was the 8586 microprocessor. Lots of fanfare, exciting, faster, better, the new technology microprocessor. Somebody noticed that a particular set of numbers, if you divided one number by the other, you got the wrong answer. The Pentium chip just gave the wrong answer for a particular division of two particular numbers. So then the question was, how much does that matter? Because if you were just picking numbers at random based on their digits, the chance of hitting the number that was one of these bug numbers was incredibly low. I mean, ridiculously low, to the point where certainly wouldn't have happened in human history with people running Pentium chips all the time. But if that number was a producible number that turned out to be really it's 6 over pi squared or something to enough digits, then much bigger deal, because one could really imagine that that number would actually show up in practice. Turns out, so far as I could ever tell, the numbers that led to the bug were not producible numbers. By the way, this term producible number, I just invented that 3 minutes ago or something. It's not a standard term in the literature of mathematics and so on, but I think it's a good term for this particular idea. So that's sort of an application of this, that's sort of an inverse numerology kind of question of, oh, there is no simple version of this number, so we don't have to worry as much about the fact that there is a bug in that case, because the chance that that number occurs is really, really small.